Our second talk tonight is going to be by Mikhail Chimentsev. He is a biogerontologist and a science communicator. So after earning his MD, he pivoted to doing fundamental research into aging, specifically connections between mitochondrial biology and aging for the last 10 years. He's also widely interested in a bunch of topics. This is his second Nerd Night talk, and he's going to tell us today about microscopy outside of the visible spectrum.
Right. Okay, thank you. Okay, let's get rolling. So, this is a microscope. Everyone knows how it works. On the off chance that you didn't get this obvious reference here, there is this medieval Polish encyclopedia that has an article for a horse, and it reads horse. Everyone knows what a horse is. So that's a microscope. You place some small object here, you shine some light on it, you look into the eyepiece, and it enlarges the object you place here. So here we have a microscopic image of some neurons, some nerve tissue. And so this is actually about as big a picture you can get from this kind of microscope. By this kind, I mean light microscope. So you can see like separate cells. You can see they have a nucleus. You can kind of see that something is going on here. There's some things inside, but they look like just blurry, squiggly things, and you wonder how do I get it bigger? How do I actually see in great detail what's going on there? So for reference, it's going to be important later. Some of these squiggly things are actually mitochondria, the powerhouses of the cell. But say if you use bigger lenses, more light, bigger microscope, everything just bigger and better, you still wouldn't be able to see the things. You would just get, okay, so getting an image bigger is actually a very trivial task. You just project it onto a larger plane, or say with your phone, you take a picture, you take digital zoom and just stretches the picture, but the blurry things don't become more clear. They just become bigger and blurrier, right? They're still just indiscreet squiggly lines. So this actually has a fundamental problem. There's a fundamental problem here. Microscopes and generally, optical equipment that lets you see things, like telescopes, microscopes, they're not about making an image bigger, because making an image bigger in and of itself doesn't help you that much to see into things. What it does is it helps you resolve things, right? So microscopes are actually all about seeing how many different things are in this single blob of blurry squiggly stuff, right? And at the very fundamental level, it's about seeing two specks, two dots, right? Two very small objects which are really close together as two separate objects, not just one blurry thing. This is called resolution, and this is what microscopy is actually all about. As long as you have resolution, you can enlarge your picture and see more and more detail, or you can squint and see in a very small picture. If it has very high resolution, you can still see. If you have low resolution, you can enlarge to your heart's content. You will just see a lot of huge pixels and stuff, right? So, but the problem here is that why do we have a resolution limit? So this is why by just using bigger lenses, bigger microscopes and stuff, more light, you don't get more resolution, because in order to see into things with these light microscopes, we use light. That's correct. And light has this special property, right, which is the light is simultaneously a wave and a particle, exactly, right? So you can imagine it is like a stream of particles, but it's also like a wave, and waves have wavelengths. So for the reference, wavelengths is distance between the peaks, between the last peak in the previous, like this peak and the previous peak. It's not the width of the wave. This is called intensity. Wavelength is distance between peaks, right? And if these specks are too close together, that the distance between them is actually comparable to the wavelength. Light kind of goes around them, and you cannot get a clear picture. They will still be, blurry. And this is the limit of light microscopy. It's called the Abbe's limit. Right. These are like our numbers. You can't really see details. You can't resolve two like separate dots if they're like closer than 300 nanometers together. For reference, like average cell is like three on the scale of like thousands of nanometers. So like small tens of micrometers, right? 1 micrometer is 1,000 nanometers. So you can see separate cells. You are able to see separate cells, but you cannot see like in great detail what's going on inside these cells. And what we do actually have some clever ways. The Abbe's limit has been breached somewhat in the like preceding decades by applying some clever optics and using some like glowing like dyes in a very specific way. We can squeeze some more resolution out of light microscopy, but every step there comes the great price. It's the complex technologies. They like take a lot of time to develop and streamline. Ideally, we want something that's very scalable. You just unlock a new principle, and you immediately increase your resolution ability a lot. So this thing here is going to be our only equation today. So please bear with me. Right. So this is what defines your resolution, your ability to resolve things, right? So it basically has two things: this thing here on top and this thing here on the bottom. This thing here is basically describes the shape of your lens, right? This is like just a fancy way to say numerical aperture. Do we have any photography aficionados here? Show of hands. Right. So this is numerical aperture. It's like from what angle does a microscope collect light, essentially. Right. So these got maxed out real quick, real soon. So our best way to increase our resolution would be to so we can either like make these change these like make these smaller or make these larger, right? So this lambda here is our wavelength, right? Which is again property of all light, right? Very important thing and very, very unique to light, right? Do you agree with me? I see some nods, right? This is what's called subtle foreshadowing. Anyway, so we want to change these things. So we want to use smaller wavelengths, right? And so just regular visible light isn't good enough for us. So what do we want to use logically? UV. Right, yeah, we got the answer UV, because ultraviolet light, it has shorter shorter wavelength, right? They're shorter, they don't get around, like closely spaced things as easily, right? So we would call that UV microscopy. Have you ever heard of UV microscopy? Right. Yeah, so it does in fact exist. It is, it's very similar to regular light microscope, with like just the basic, structure here. There are like just basically two changes. Instead of visible light, you have an ultraviolet light source here, right? And so regular glass is actually opaque to ultraviolet light. And by regular glass, I mean like glass doped with like sodium and all this like window pane glass, right? We need to use the glass you make in Minecraft. So just pure sand, molten and shaped into glass. It's called fused silica. It's just pure silicon dioxide, right? The glass is actually transparent to UV light, and that's about it. And important distinction here: some light microscopes do use ultraviolet light to shine onto the sample, but this sample is like dyed with fluorescent dyes. So this UV light is used to make these dyes shine in invisible light. They activate the dyes. They re-emit the photon in like invisible light. Lights are available to our senses. So this wouldn't be UV microscopy. This is called fluorescence microscopy. You only use UV to make your dyes shine. These guys, they straight up just use UV to see things. And obviously, you cannot see UV, so you will need some like fluorescent plate or like a camera, the matrix that is capable of seeing UV, and you do get, more details. You can see that like inside the cell, you start seeing this, more smaller things. But these, we pretty quickly we max out this thing as well. And our next step would be, so UV is not enough for us anymore. What do we use? Huh? We got microwaves. What other? What does it mean, sir? Huh? X-rays. Any other ideas? Yeah, we do in fact use X-rays. So, anyone ever heard of X-ray microscopes? Oh, you have, right? Great. Huh? Ah, yeah. So they are used in crystallography, but there are actually just X-ray microscopes that are used for imaging. You place a thing in there, it shows you a picture of the thing. These are our numbers. It has like way higher resolution. You start seeing like the largest protein complexes. You can see, organelles in great detail. You can see like different, like you can see the squiggly things inside mitochondria with this thing, right? So these are like the examples. So here you actually see, the cells like we saw on previous slides would be like this, right? And you can see that, the structure inside mitochondria. You see the cristae, right? So great. There are a couple of problems though. So X-rays are good at penetrating matter. Everything is transparent to them, which might be a pro, might be a con, depending on your circumstance. However, X-rays also have another property. They are very, very hard to bend. Once you emit an X-ray, it flies straight, more or less straight path, and it's very hard to, not diffraction, what's the word? Bending. The science word for bending is, anyone? Refraction, right? So X-rays have very low refraction coefficient. You cannot easily make a lens for X-rays, right? And lenses is what the microscope, hinges on. Otherwise, you just have a flashlight. So there are a couple of ways. So the first one, you actually forgo lenses. There are different types of devices that can bend light by using diffraction. Different thing. It's you remember double slit experiment where you throw things and they suddenly some pattern and not what you expect them to be. So that's diffraction. And you can use these basically like grids or like plates with slits in them to change the trajectory of light. All right, they have rather poor properties as lenses. They're poor substitution for lenses, but better than nothing. But eventually, people realized you can use. So this is an X-ray lens. So this is just void, and this here is actually aluminum, also known as aluminium. And since aluminum is transparent to X-rays as pretty much everything, and it can still slightly bend it when you stack several aluminum lenses on top of each other. Each of them bends an X-ray a little bit, and eventually you can focus it and use as lens in your microscope. This is still a rather, non-trivial arrangement, which is likely the reason we don't hear about X-ray microscopes as much, because in the course of development of our technology, we actually arrived at a much simpler solution with something that isn't so finicky to bend. That would be what other type of big, cool, powerful microscope do we know? Right, so everyone knows, it was in the description, but I fully expect that pretty much everyone has heard of them. So yeah, this is why electron microscope is something everyone hears about. This is not an electron microscope. This is what it looks like. So it's like from a sci-fi video game. It's called Subnautica, if you're wondering. But there is this idea that it's about future. There's like spaceships, so everything should be cool and advanced and very powerful. And electron microscope, it kind of gives you a window into general psyche. An electron microscope is just like microscope, but better and cooler and stronger. Like first you smell copper, then you smell iron, then you smell titanium, because titanium is better, right? Anyway, so there's no person who drew it is really interesting to me, because you can see the person who made this had this idea but had no idea what an electron microscope looks like, because as you will see, no way in hell you get these to work. So this electron microscope, ignore all these bits. This is the main bit here, creatively known as the column of the electron microscope. The principle is actually the same. You have your small object, you shine not light on it, not light gets bent and focused, and a series of lenses creates a larger picture. So general principle is very, very similar, except that electrons are not light. Then you might ask, how the hell would you bend it? Because and how do you produce not forget bending, how do you even produce an image? How do you resolve these small specks? Because if you need a wavelength to not go around them and produce a high resolution picture, electrons aren't light. How do they have a wavelength, right? So it turns out that a beam of electrons does have an effective wavelength. So this is called a de Broglie wave, and this is it gives you the wavelength of your electron beam, which is defined by Planck constant. It's called constant because you can change it. You just bite the bullet and deal with it. The only thing you can change here is this. This is basically energy, right, or acceleration of your particles, right? So, fortunately, electrons are what electrical current is made of, and we know very well how to deal with it, right? You just apply stronger voltage to push them, to give them a stronger kick, right? Like this analogy that the current is like water flowing through pipes, right? And like, what do you call it? Voltage. What's the other word for voltage? Voltage. You just call it voltage, right? Voltage is like a pressure of the water inside that pipe, right? So you push it real hard, you accelerate the electrons from here. This thing is called a filament. It's like cathode. Something that emits electrode under huge pressure. The huger the pressure, the faster the electron, the smaller the wavelength. And this electron de Broglie wave has an effective wavelength of about 1 to 4 picometers. This is what limits your resolution. So as you can see, as opposed to a light microscopy that has about 300 to like 250, X-ray has 20. This has like way below in a single nanometer, right? So your resolution is basically unlimited. Fundamentally, you can see like separate molecules. You can see even like some larger atoms, right? Okay, so you can actually see a single atom with your naked eye, but it's a different story. But in order to see arrangement of several atoms, you do need something like this, electron microscope. Right, so there's actually a lot of things electrons do and can tell you about stuff. So an electron beam, like impacts, right, some piece of matter. Some of them get reflected, some of them get re-emitted in a lot of fancy ways that tell a lot of stuff. Some of them actually fly right through. This is what we usually use in electroscopy, which is why it's called TEM, transmission electron microscopy. They get transmitted, means fly right through. So you have your light, right? You have your transparent is going to be important later, piece of matter, and you like see what shines through, right? What is transparent to electrons and what is not transparent? So nothing is really transparent to electrons. That's the problem. Most matter is opaque to electrons. This is why in this like column of electron microscope, you actually need very strong vacuum. So there is like pump that always pumps out air, because otherwise the beam would not get through, right? But another problem with that is that organic matter, right? Which we often see in study using electron microscope, is rather uniformly intransparent. So there are no bits and pieces that are differentially transparent to it, right? So what we actually need to do is stain our sample, our organic sample. Some like people study like metals using the microscope. In this case, like small slice of metal. In this case, you don't need to stain it. It can stain itself. It's its own safe stain. But organic matter, you need to stain with something that is very good at stopping electrons, which is metals. Ideally, heavy metals. The ones that are commonly used are osmium, lead, and uranium. Very safe, very nice, safe job. Right, so you have your stain piece. You embedded in resin essentially to help you cut it. You cut it on this thing called ultra microtome. This one in particular is called ultra cute, which I appreciate a lot. So you using this special knife. So this actually diamond knife is literally like diamond. It's used to cut because metal is too soft. It won't give you a thin enough slice, right? And you place it on your sample holder. It looks like it's from 1870s, right? Like, these old-timey divers probably use this kind of stuff. Anyway, so, and this is kind of picture you get. You can see pretty much anything you want as long as it actually sucks up osmium, right? So when you see electron microscope picture, you actually see a distribution of osmium atoms. Things that aren't good at sucking up osmium, blend into the environment, like into the background, right? So some things we cannot see, not because they're too small, but because they don't stain that well, right? Okay, real quick. Electron microscopy has a lot of issues that you see in light microscopy, just to underscore how similar they are. You have chromatic aberration. Chromatic is like this, means colorful. You have different colors of electrons. They get bent different. Get bent sounds wrong. Sorry, English is not my native language. Different colors of electrons. You can fix it. Long story short, there is another cool thing about another cool variation of electron microscopy called cryo-electron microscopy. It's commonly used to study structures of proteins, but it's not exactly, it is still imaging, but okay. Another cool thing about it is that it preserves the tissue real well. Some details you will lose when you fix your tissue with a electron microscope. So there's like gaps between bits of nervous tissue. When you freeze it, you need to freeze it real quick. You need to vitrify it with separate single molecules. You just plunge it into liquid nitrogen. With the tissue, it won't work. It will start tearing apart. You need to do it under 2,000 atmospheres pressure. Special freezing chamber. Provides a lot of detail though. So this is like a bit a larger story, so pardon me for probably delaying the end of my talk, but I just want to go through it. So with light microscopy, if you remember the chart I showed you, it says thickness limitless, or like about several millimeters based on how transparent your tissue is. If the tissue isn't transparent enough, you make it more transparent. Light microscopy gives you this cool 3D microscopy of the piece of tissue. Electrons are bad at permeating matter. It's hard to make a 3D image. Here you just move your focal plane and collect a lot of images. Light microscope, your focal plane is the thickness of your sample, 65 or so nanometers, right? So what you ideally want to circumvent, because as just a single slice through the structure doesn't give you a whole picture, right? This is why some people think that mitochondria are bean shaped. Some are, most are not. They are a network that goes all through the cell, but when you cut through the cell, you see a single slice which is kind of bean shaped. So you want 3D-fy your image. The easiest way is to make a lot of slices real close together. The upside is it's very easy, very intuitively available. The downside is if you mess up one slice, the whole sample is more or less ruined. I've been there. Need to be real accurate here. A bit more complex way, you insert the cutting thing right inside of your microscope, and you don't shine through, you actually reflect your electrons, but it's still the same pattern, so you see the same picture, called serial block phase scanning. Well, it's written right here, right? Something else, it's pretty much the same but sounds real cool. It's called ion mill, ion microscopy. Instead of a knife, you use a beam of ions that chip away your sample, revealing increasingly more deeper layers. Yeah, you mill down, you take a picture, you mill down, you take a picture, something from Star Trek. Electron microscopes are older than Star Trek, so we were there first. Anyway, another way, you're basically circumventing the problem that electrons don't pass through matter very good. This is because you are not giving them enough incentive. If brute force doesn't work, you're not using enough of it. So you have this ultra high voltage electron microscopy. This is actually the same thing. This is the top of the thing. This is the bottom of the thing. This is how it looks together. A regular electron microscope uses accelerating voltage of about 80 to 120, 200 kilovolts. This one uses 3000 kilovolts, also known among friends as 3 megavolts. Gives you just a 3D image of the whole cell, but you need to tilt it a bit to get, better image. This is something you can get with 3D electron microscopy. This is also something you can get through a 3D electron microscopy. So there is a certain story we can see like unfolding. Some people who followed it could have seen unfolding over the last 10 years. So there was a project called iWire, where people would create a sample of retina, right? Mouse retina, I believe. And so they created the entire retina. They sliced it so that they have like a collection of slices of the entire thing, right? They took an electron microscope picture of each of them. The idea was to trace. Retina is basically a piece of the brain, right? It has the same structure. It's the same kind of, wires emanating from neurons that wire together, and it's structured the same as the brain. The idea is to trace every single process, every single wire inside the retina. Not because we're particularly interested about the retina, we were, but also because it could be later used for the brain, for the rest of the brain, because again, the retina is a piece of the brain, the central nervous system. So AI wasn't that good back then, so they actually created like a citizen scientist platform where you could play this kind of game where you don't manually do it, you help a nascent AI, you train a nascent AI to trace these processes through different slices. So this project ended with some results. So next thing you could see is actually they did the same thing, but now with a piece of actual brain cortex. So it's a very, very small. You could have seen it's like basically smaller than a body of a neuron, right? But you could see inside of it every single wire in great detail. Again, this resolution is only obtainable with something like electron microscopy. There's a lot of computational work here, a lot of computer science, AI work, but also electron microscopy. Okay, so now we have a piece of the brain of actual real thing, right? But 2 weeks, October the 2nd, it's about 2 weeks ago, right? Came out an article where they did the same thing, but for the entire fly brain. It's a bit smaller than mine. But still, the entire brain, imagine an entire brain with all its not only neurons, but every single tiniest cable that comes out of these neurons, traced, catalog, map into a single database. This thing they say is 100 teravoxels. Transform it into terabytes yourself. It's going to be your home assignment. So they are also actually done this with the fish. This is just the imaging. They only done the imaging in 2017. I'm pretty sure they're doing. It's called connectomics, right? So you trace all the connections of all the neurons. But we have a fish. A fish, unlike a fly, is tasty. Is a vertebrate, just like us. So this, a step in our direction. Real quick, couple small things. I'm mostly done. I wouldn't be if I had more time, which I don't. Electron microscopic pictures you've seen so far were either black and white or painted or artificially, because even though electrons can have different lights, they are not different enough. They don't, reflect off of different things differently enough to produce colorful picture. It's not usually a problem in science. We're not here for pretty pictures, even though they're nice, but you still miss some information. They have developed a color electron microscopy. How do they do it? Electron microscopy uses dyes which are heavy metals, use heavy metals different enough so that they reflect different electrons. These are compounds containing lanthanoids. Lanthanoids sounds cool. This is why I'm showing you this picture. Next picture, scanner microscopy. You may have seen these kind of things. Scanner microscopy sometimes used to produce pictures of bigger objects, bigger than single like organelles, mitochondria. Still looks cool. Gives you a great a lot of details. Also, it is just inherently three-dimensional because you shine on three-dimensional things and they reflect every which other way. Just use a bigger detector. You can also see it has about as much resolution, so you can actually see internal structure of things. It's very cool. You cannot actually stick a piece of living tissue in scanner microscope and just see this picture. There's a lot of cool steps you need to do, but I don't have enough time. Short story, cryogenic preparation and metal coating. Also can be used in material science, computer science, this kind of thing. Interesting story. My mother used to be a steel worker and she worked with electron microscope in her line of duty, which I only learned after I started working with electron microscope. I guess it is congenital, inheritable. Right. Anyway, so subtle foreshadowing comes to closure. Turns out not just electrons display wave-particle dualism. So it would be believable if only photons did that. Now that we know that photons and electrons do this, and they're completely different kind of particles, you can start suspecting if it's that unique. It is not unique at all. All streams of particles of matter display wave particle dualism. You can shoot a stream of ping pong balls or regular tennis balls or football balls, soccer balls, sorry, football balls, and they would have a wavelength. People shot a lot of stuff at the distance, and they all display certain wavelength, which is why everything can be turned in a microscope if you're brave enough. Muons are like electrons but heavier and don't live as long. I'm not sure why this thing in particular is useful, but muon microscope sounds cool, which is why it's here. Proton microscopes are also a thing. It's highly experimental technology. It doesn't have a lot of applications being developed. It doesn't provide like extremely good resolution, but protons are heavier than electrons. If you keep them strongly enough, they will pierce through the matter. So you can use them to image in real life live tissue inside a living person, if you wish. Usually people are advised against being shot at by a proton beam. However, there is actually an anti-cancer surgery called proton knife, where the stream of protons is piercing the focused upon a tumor. And proton microscopy can be used to also get the image and aim it better. Another cool thing that has wavelength is sound. I really wanted to be called sonic microscopy. It's called acoustic microscopy. Has some unique properties which I don't have time to talk to you about, but I promised in my description that I will mention a lot of types of microscopy. Acoustic microscopy also a thing. If it has a wavelength and exists, it can be turned into a microscope. Actually, pretty good resolution. And yeah, also acoustic microscopy. And the last one, again, everything can be turned into a microscope if you are brave and daring enough. Every imaging technique, including MRIs right now have sub-millimeter, like fraction of a millimeter, but like half a millimeter resolution per voxel. But if you cleverly construct a very precise MRI machine, you can make an MRI microscope that will show you like separate cells. This blank slide concludes my presentation. Sorry I took too much time. This will happen again.